Okay, good morning. The continuation of the lesson is about the second derivative and concave and convex functions. Okay, so we want to use the notion of derivative to understand extra properties of curves. Yes, so you know that in principle I can have a function of this form. Yes, it's like an upside down bowl, or I can have a normal bowl. Yes, something like this. Okay, of course you know that this point is a maximum point, this point is a minimum. But if I can have a little bit, if I want to stop before that, still there is a difference between this graph and that graph. Not because this has a maximum or minimum, but you see that the curvature here is different from the curvature here. Yes? So what is the difference? Here in this case, if I choose any point on the graph and draw a tangent line there, in the vicinity of that point, in the neighborhood of that point, the curve lies below the tangent line. But if I do the same thing here, what happens if I draw a tangent line here, then close to that point at least, the curve lies above the tangent line. So that is the main difference between these two things. Okay, we say that this curve at this point is concave. And we say that this curve at this particular point is convex. Okay, I usually mix these words. These are the words that you use in your book. I am comfortable to say that, okay, this is concave down and this is concave up. So this is also something that books use actually. But the book uses this, your book uses concave for this kind of behavior and convex for that behavior. Yes? Okay, so how can I understand the behavior, such behavior for my function if I do not have access to the graph of the function? So that's exactly the same thing we want to do today. And then you realize that the notion of the second derivative comes into the game. Yes? How is that? Let us try to understand this problem. Just for example, for this case of concave. Yes, let me see if the convention in your book is that. Yes. So this is convex. Yes, that's correct. Okay, so here, let us consider the case of actually, let us consider the case of the convex one, for example, something like this. And I want to see if my graph at this given point, say that the x-coordinate of this point is A, and I want to know if my graph is convex at this point or concave at this point if I do not have access to the graph of the function itself. So how should I understand that? So I need to understand what is the behavior of my function at the points very close to A. So for example, let us see what happens if I take a point very close to this one and I draw a tangent line here. Okay, this has some k value. Okay. For example, this has a k value. But if I go closer, what is happening to this k value? So if I draw this one again, yes, so let me just highlight it here. So first I have this tangent line here, but when I get closer, the tangent line becomes a little bit steeper, yes? This is what I want you to understand in this picture. Might be it is hard to draw with hand, but my point is that as you get closer and closer to point A, the slope of this tangent line is getting larger and larger. Yes, is that clear? Okay, so this means that if I have my function convex at this point, then this behavior is more or less understandable. So the slope of the tangent lines at the points in the neighborhood of that point are constantly increasing. Is that clear? Somehow intuitively. Okay, so what does it mean? Let us now be a little bit more careful. So let me just take this representative, this point with x. For example, let us assume that the x coordinate of this point is denoted by x. Of course, in this case, x is this one. When I get closer, x is that one. Then the slope of the tangent lines, I call them k. I hope that you agree with me, it is a function of x. Yes? Because when I start changing this x, the slope of this tangent line starts changing. So this means that the slope of the tangent line is a function of x itself. Okay? But if I ask you to calculate this, you already know what to do, yes? If I ask you to calculate the k value of the tangent line, what do? Assuming that this function is f of x, you differentiate the function and then calculate the derivative at the x coordinate of the point of tangency, which in this case I called it x. So this is nothing just new, you know that the k value is equal to the first derivative. But on the other hand, we just realized that k is an increasing function of x. I didn't prove this statement rigorously, but this is intuitively very clear. Yes, at least for these very well-behaved functions. Yes, is that clear? So what is the meaning of this? You remember what is the meaning of an increasing function? It means that if I increase the value of x, the value of the function also increases. So this means that my function is increasing. So we just learned that when I increase the value of x and getting closer and closer to a, the slope of this tangent line is increasing. This means that the k is a function of x and it is an increasing function of x. Okay, but now if you know that it is an increasing function, you know something about its derivative. What is the derivative of k then? The k prime of x is positive because the function k itself is increasing. Okay, but then it is clear what is happening. So this means that k prime of x is f prime of x. If I ask you what is, k of x is f prime of x. If I ask you what is k prime of x, what is k prime of x? It is the second derivative of that function. Yes, what is the meaning of second derivative? It means that you differentiate once, you get a function, you differentiate it again to get a new function. For example, if I give you f of x equals to x to the power of 3, if I ask you what is the first derivative, everyone knows that the answer is 3x squared. Now, if I ask you what is f double prime, the second derivative of f, it means that first you calculate the first derivative. When it is done, it becomes a new function. Now treat this as your function and start differentiating once more. So the answer to this is just simply 6x. So that's the meaning of second derivative. Second derivative means the derivative of the first derivative. Okay, so this means that if k of x is f prime of x, because I realize k prime of x should be positive because k is an increasing function of x, then k prime of x, which is f double prime of x, means that f double prime of x is positive. So I realize that if I have this property of the curve that it is convex at a point, in the vicinity of that point, everywhere, call it x, the second derivative is positive, including the point A itself. Okay? So this is why we now know this behavior. So if f double prime of A is positive, you should expect this behavior. And if f double prime of A is negative, you should expect this behavior. Yes? So this is something you should have in mind based on this intuitive argument. Okay, so now if I go back here, so this theorem that you see here, convexity and the second derivative, consider the function f on an interval I. If f double prime of a is positive, then the function f is convex about x equals to a. And if the f double prime of a is negative, then the function f is concave about x equals to a. So sometimes I use concave up and concave down. It is easier for me to remember which word represents which situation. Okay, any questions so far? Okay, now we solve two examples here. Determine the intervals on which the given function f is convex or concave. Okay, so whenever you want to say something about convexity or concavity, you need to remind yourself about the second derivative. Remember when we wanted to talk about local maximum and minimum and terrace points, they have something to do with the first derivative. So you need to know that when you want to talk about convexity, you need to know the second derivative. And the notion of second derivative is not complicated. You differentiate once, you get a new function, you treat that function as if it is your given function and differentiate it once more. Okay, so let us just do this example. So we want to determine the intervals. So in other words, I want to know on which interval this function is actually concave or convex, both of them. Okay, so let us go back to the board. So f of x, x to the power of 6, x to the power of 6 minus 10x to the power of 4. Okay, so now according to the lesson, you know that I need the second derivative of this function. I cannot calculate the second derivative unless I have already calculated the first one. So this becomes 6x to the power of 5 minus 40x to the power of 3. Yes, and then I differentiate it once more. It becomes 30x to the power of 4 minus 120x to the power of 2. Yes? Yes.
Isn't there a very simple formula for second derivative?
No.
It's not?
No. Okay, so if I want to know where this is positive or where this is negative, the natural step is to know where this is 0, yes? Or if you want to, you can, it's very natural to ask yourself when this is 0, okay? So I'm asking for where this function becomes 0, because when I know when it becomes 0, I can know better when it is positive or when it is negative, yes? So if I want to do that, I hope that I'm not confusing. Anyway, so let us just say for convexity, okay, convex. So convex happens if the second derivative is positive. So this means that the 30x to the power of 4 minus 120x squared is supposed to be positive. And then you need to know the values for x, which guarantees this inequality. But it seems hard, but it is not, because you can easily factorize this. So you can say that this happens if and only if I can factor 30x squared out, and then this becomes x squared, and then this becomes minus 4. Yes, I want to make this positive. Okay, can you tell me where it is positive? You want to choose all possible values for x, which guarantees that this expression is positive. So 30 is already positive, so you don't have any problems with that, yes?
X has to be above 2.
No. Because I repeated this several times. Yes, you need to learn that finally. That is one scenario. When I say solve, it means I am caring about all possible scenarios, yes? So first of all, 30 is positive, so I don't need to be worried about that. I want to make this product positive. 30 is positive, x squared is non-negative, so I have to make sure that x is not 0, because if x is 0, then it becomes 0, which is not acceptable. So anyway, I don't need to be worried about x squared that much, because this part is non-negative. So to make this positive, I have to think about how to make this positive. Yes? So I have to make x squared greater than 4. But x squared greater than 4, we have talked about this several times. If you just write x greater than 2, it is not wrong, but it is not complete. Because there are other numbers that this also satisfies with.
Or less than minus 2.
Or less minus 2. So you should say that, okay, this happens if and only if x is less than minus 2 or x is greater than 2. Yes? So it means that on which intervals my function is behaving like a convex function, the intervals from minus 2 below and from 2 above, yes. So for example, if I want to imagine something, so if this is minus 2 and this is 2, on this part, the graph should be convex, so it should be like this, and then again, after that, it should be like this. We will draw the graph, you will see that. Okay, but then the concavity is easy now, because if it is not convex, it is concave, yes? So it means that concave, so where do you think the concave is? Yes?
Between minus 2.
Between minus 2 and 2, yes? So this becomes between minus 2 and 2. Because if I am on the left side of minus 2 or on the right side of 2, the function according to this calculation is convex. So if I ask you where the function is concave, it means neither that one nor that one. So what is left for you is the interval in the middle. Okay, so that would be interesting if we also draw the graph and check it clearly, okay? Okay, so what the function is, y is equal to, but the powers are so big, I hope that we are not in trouble by Geogebra, but anyway, 6, and then I go down, minus 10. By the way, before just going further, so I hope that you see that this function is concave up all the time. So it is convex all the time, yes? But now if I increase, so if I add that minus 10x to the power of 4, so the function becomes like this, okay? And yeah, to understand this a little bit better, so let me rescale it a little bit so that, yeah, sorry, here. And then let me also increase this. Yeah, now it is seen better. Okay, so what is happening? So according to our calculations, exactly what is happening at minus 2 and 2. If you want to, I can draw these lines so that you can see this better. So this is one of them, and then I have x equals to minus 2. That is the other one. So I hope that now you have this feeling clearly that, yes, you see, if I go to the left of this black line, I hope that you see that the graph is always concave up. It's like a bowl, it's a normal bowl, yes? And even if you go to the right of 2, it is still like a normal bowl, but between these two black lines, it is like an upside down bowl. That is the way that we can understand using this. And then, do you know what was the name? I don't know if I have talked about the name of this point here before, yes?
The inflection.
The inflection point, exactly the point at which this behavior changes. Before that, it is concave up. After that, it becomes concave down. Even this one is also an inflection point, because before that, it is concave down, and after that, it becomes concave up. So these minus 2 and 2s are exactly those borders in which the property or the behavior of the function changes. Is that understandable? So this is what we actually calculated. Is that clear? Yes or no? Okay. So let us solve another problem together. So if I think it would be a good idea if I pause and wait for you, okay? So the second example, the same scenario, yes? This is a function. I want you to know where the function is concave up and when the function is concave down. I give you 2 or 3 minutes. It's not that hard, and we can continue. Okay, did it work? I don't think it is hard, so let me just continue so that we can cover what I'm supposed to do. So we want to find the behavior of this function regarding to convexity or concavity. Okay, so the function is this function. So you know that whenever you are talking about concavity and convexity, you need to know about the second derivative. So I will do the first derivative. It becomes 4x to the power of 3 minus 6x squared. And then I do once more. It becomes 12x to the power of 2 minus 12x. Okay, so I need to know where f double prime is positive and where it is negative. Yes. So for example, for convex, I put f double prime of x positive and then try to solve that inequality. Of course, the inequalities that are given are not that hard. So if you have a good understanding of what is the meaning of an inequality, I think you can solve that. So how can I solve this inequality? For example, it might be motivating that if I take 12x out, might be it is easier, because when I see a product, it is always easier to say when it is positive and when it is negative. So this becomes x minus 1. I want to make it positive. Okay, can you tell me when this inequality holds? All possible points where this inequality holds. Yes?
When x is greater than 1.
This is it the whole story? Yes?
Also when it's less than 0.
Yes, because you see that 12 is always positive, so you don't need to be worried about that. You want to make this product positive. When this happens, under 2 circumstances, yes, either both of them are simultaneously positive or both of them are simultaneously negative, something like that, yes? But when this happens, you say x should be greater than 0 and x should be greater than 1. Do I need to emphasize on being positive? No, because when x is greater than 1, it is automatically positive as well. So instead of 2 conditions, I can summarize this one to 1 condition. And that is what you mentioned, actually. But here, x is less than 0. The other meaning is that x is less than 1. Okay, I have x less than 0 and x less than 1. Do I need to emphasize here that x is less than 1? No, because if x is less than 0, automatically it is x, it's also less than 1. So this means that this reduces to this one, and there is the or between them. This is one way of understanding that. Another way of understanding when it comes to second degrees is imagine the graph of the function. So if I ask you what are the roots of this polynomial, which is of second degree and it's a parabola, so you know that the roots are 0 and 1. So for example, you go to a scratch work and then you see that you have 0 and 1. These are the zeros of my function. So the parabola should be of this form or of that form. Which one is that? For this case, because 12, which is the coefficient of x squared, is positive, you know from your previous studies that this should have a minimum. So this is not the graph of this parabola. The graph of this parabola is of this type. And on the other hand, it should pass through these 2 points. So this means that this is somehow the way that you can imagine. But you are interested at those points where this parabola, this polynomial is positive. So it means the graph should be above the x-axis. So do you remember, here is 0, here is 1. I want to have the graph above the x-axis. So this means that either I should be on the right-hand side of 1 or I should be below 0. Yes? For quadratic equations, this is also always possible. So anyway, in any way that you want to conclude this, we conclude that x should be where? less than 0 or greater than 1. And then if I ask you where the function is concave, of course the other, what is left for you? What is that?
Between 1 and 0.
Yes, and so f double prime x should be negative, so this means that x should be between 0 and 1. Yes? So that is the answer to the question, and this is very simple. It is also, oh, unfortunately, I forgot to switch the camera. Anyway, so let us go to Geogebra and see how is it working there. So the function, let me just get rid of these. We don't need them anymore. Okay, so the function is y equals to x to the power of 4 and then minus 2x cubed and then plus 1. Yes, so that's my function. Okay, so this is very strange behavior. Can you see that what we have done, the calculation is right or wrong? If you see this graph, yes?
It's slightly...
Yeah, because I have to rescale. Might be this gives you the wrong impression that the graph is always concave up. Because if you don't know about this thing before, might be this give you the wrong impression. And actually that's the power of mathematics. So let us go back home. That's the real graph of the function, okay? And then which points are crucial here? 0 and 1. So you see that here is 0 and here is 1. I don't know, can you feel that this is happening? So you know that when I go to the left side of 1, when I go to the left side of 0, you see the behavior of the function is always concave up. And even if I go on the right hand side of 1, the function is always concave up. But between these 2 points, the function is actually concave down, yes? So I don't know, might be it is a better idea if I want to rescale it a little bit, you can see it better. Is that understandable? So that is what we actually calculate when we want to talk about concavity. Okay, so then let us go back to the notes now. And this is the definition of the inflection point. We already discussed about that informally. So consider the function f and the point A with coordinates a and f of a. When I say a and f of a, I mean that this point lies on the graph of f. The point A is called the inflection point. Inflection, again, is pronounced in English, but that is a British way of writing inflection. It seems like French word inflexion or something, but when I check the Webster Merriam dictionary, this is the British way of writing inflection, according to that, okay? So we say that A is called the inflection point of the function f. This I want to emphasize, yes? If A is not a sharp point on the graph of f, which is not given in the book, but I want you to understand this one as well. F is convex on one side and concave on the other side of A. That's exactly what you need. What I added today is just this thing. Why do you think it is needed to add this? Because in the book they say that, okay, the convexity or concavity changes when I pass through this point, and I use this myself, okay? But I just want you to understand that there are some exceptions that you have to be a little bit careful, not at the level of high school, but for the other functions. So why do you think it is necessary to emphasize that A shouldn't be a sharp point in the first place, and then we have this property? Yes?
Because we know that a sharp point, we cannot draw a tangent line on the sharp
Okay, but because the way that we say, but we can still think about change, the concavity changes, yes? So because the main thing about the inflection point is the change in concavity of the function, yes? In other words, can you imagine a sharp point, but the concavity I mean, this is, let me just draw a picture for you. So if I have this one, and then I have this behavior, yes? So let me just draw it in a function. Okay, so here, if I say A, I don't know, do you feel that this should be called an inflection point? But still it has that behavior, yes? If I ask you what is the concavity of this function, is the concavity of the function changing in passage of A? The answer is yes, because before that it is concave down, and after that it is concave up. But this we don't consider to be an inflection point, yes?
Maybe that almost feels like a matter of definition, like if you want to consider this in an inflection point.
Yes, but that's what I'm saying, because the notion of inflection point makes sense if the notion of the tangent line changes smoothly. Okay, so in that case, even though you see, if I ask you what is the concavity of the function before that, you say it is concave down, and when I pass this line, it is concave up. Yes, so it actually satisfies that crude definition of the inflection point, but we want to exclude this type of behavior as the inflection point. That is something just I want you to know, okay? Okay, so and you already know that every terrace point is also an inflection point, not the other way around, yes? So if I go to a terrace point, so you know that a terrace point has extra property. So it is not only an inflection point, but also in a way that the tangent is also horizontal. So this is the terrace point, but you can also say it's also inflection point. Why? Because before that, for example, the function in this case is concave down, and then immediately after that, the function is concave up. Yes.
Why don't we include point A as an
Here,
yes?
that is, there is no why, because we don't, because it's a good question. That is by the definition of the inflection point. So if I say that is this an inflection point, we choose not to consider this as an inflection point, even though before that it is concave down and after that it is concave up. Because if you want to find the inflection point, you need to calculate somehow the second derivative. So we will say that the second derivative should exist. That is the definition. If you go to higher text, the definition of the inflection point is that the second derivative exists. But the second derivative cannot exist if already the first derivative does not exist. And the first derivative does not exist, that is the lesson before, because that's the sharp point. Okay. So let me just read this recipe for you. Okay, let me ask you before showing the recipe. So how do you think if I give you a function and I ask you to find all possible inflection points of that graph or that function? Can you tell me step by step what we are supposed to do? Hmm?
I guess you need to find all the ranges where the second derivative is positive or negative first.
Okay.
That would be my first step, I guess.
Okay, but inflection, because in that case you get an interval, is as we did here. But inflection points are isolated points.
Oh, would the derivative of the inflection point be 0?
The second derivative at inflection point, if it exists, should be 0. So that is the recipe. So what you do, but that's also, there are some things that I want you to know. So determine f prime, determine f double prime, yes, and then solve f double prime equals to 0, because I am looking for those points that f double prime is 0. When you know that when your function is 0, it means that if you go a little bit to the right and a little bit to the left, the function becomes positive or negative, because the borders we already found. But this is what I want to emphasize again. There is no guarantee that if you solve this equation, you get inflection points. This is the wrong impression. I want you to understand that this is not always correct. This will give the possible candidates for inflection points. Okay? And then if I want to understand if these candidates are real or not, what should I do? I need to determine the sign of the second derivative. So I need to set up a table like this. Yes? So I set a table exactly like the sign table, but the difference is that the second row is f double prime rather than f. And then what you do, you determine the sign of the second derivative to the left of a and to the right of a. If the second derivative has different signs, then yes, this point that you found is actually an inflection point. So in that case, this is an inflection point. In that case, it's also an inflection point. Why? Here, the second derivative is negative, so this means that my function is concave down. And here, the second derivative is positive. It means that everywhere here, the function is concave up. And it means that in passage of this line, the concavity of the function has changed. So this means that this is the inflection point. The same explanation holds for number 2, but it might happen that the second derivative is 0, but on the left and on the right, both of them I have concave up, or both of them I have concave down. In neither of these cases, that candidate is a real inflection point. I give you examples that this really happens. Not very for complicated functions, for very simple functions. Yes, please.
Isn't it possible that it remains at zeros on both sides?
No,
But
because if the second derivative is 0 on the left, on the right, and on that function, the second derivative is 0, it means the first derivative is just a constant. Yes? Yes, in that case you are right, if I have a straight line. If I have a straight line, then this can happen. But of course, for a straight line, we don't talk about these issues. But that is in principle technically possible. So is that understandable, the content here? So let me now start solving some questions together. Okay, so let us solve this one. This is something I want you to know. Determine all inflection points, if any, of the given functions. Yes? So I give you some examples. Let us do some of them. For example, let us start with this one, which is very famous. I give you a polynomial equation, and I ask you find all possible inflection points. But I really want you to understand, because sometimes this is a mistake. When people want to find the inflection point, they just take the second derivative and put it equal to 0, and whenever they find the answer, they say that these are the inflection points. But I want to warn you about that. Some of them are not real, some of them are fake, yes? You have to be careful about the molds, yes? Okay, so let us calculate this. I have given you a function here, f of x is equal to x to the power of 3, and then I have plus 3x squared, and then I have plus x minus 2. Okay, so how should I do that? According to what we learned, I need the second derivative, but to determine the second derivative, I have to calculate the first derivative first. So this becomes 3x squared plus 6x plus 1. I take another derivative, it becomes 6x plus 6. And then I equate it to 0, but it is not guaranteed yet that what I get is an inflection point. So I put this equal to 0 and I solve it. So x becomes negative 1. If I ask you what I've got so far, you would tell me x equals to minus 1 is the only candidate for the possible inflection point of this function, but it is not guaranteed yet that if this is the real one or not. How should I guarantee that? I need to set up a table. It's very like the previous table, but the difference is that in the middle row, instead of having f prime, I have f double prime. That's it. And then I put my number that I found here, The second derivative is 0 at this point. Okay? And then if you want to write something in here, what should I do? I need to put minus 1 into the original function. Yes? Not because you see this is the line for function. So let us do it here. I put minus 1 everywhere here. So this becomes minus 1 plus 3 minus 1 minus 2. So this is gone. So it becomes coincidentally the same. Okay, now I ask you, what is the sign of the second derivative? This is not a hard task. You see the second derivative is in front of you. If x is exactly minus 1, the second derivative becomes 0. What is the sign of the second derivative if x is smaller than minus 1? Exactly the same strategy works because that's a continuous function. So I choose a random point here, minus 2, and put it here, so this becomes negative at the end. And then I choose a random number after minus 1, the simplest one is 0. I put it here, it becomes 6, which is positive. Okay, so be careful, do not put the arrows, because arrows for increasing and decreasing. There is no guarantee that my function is decreasing. This is the second derivative is negative. Yes? Okay, so this means that here the function is concave down, and here the function is concave up. Now I ask you, is minus 1 really an inflection point? The answer is yes, because the concavity has changed. So the inflection point is usually denoted by I. So I would say that I, whose x-coordinate is minus 1, and the y-coordinate here coincidentally is minus 1 again, is the inflection point. Yes? Is that understandable? Okay, so let me go to the next one. Hopefully the next one I have designed in a proper way. So I just want to highlight this point that sometimes you get fake candidates, so you have to be careful about those. Okay, so the second function that you see here is f of x equals to 10x cubed and then minus 3x to the 5. Okay, so the recipe is again clear. So I want to find inflection points, if any. By the way, after this is finished, we can do them with Geogebra to understand this better. So here I take the derivative. This becomes 30x squared minus 15x to the power of 4. Yes, am I right? Yes. And then I take another derivative. So this becomes 60x minus 60x to the power of 3. And then I put this equal to 0. This means that I get 60x minus 60x cubed equals to 0, but you know that the third degree polynomial, if I succeed to solve it, I have to factorize it. But the factorization is extremely simple. I can factor a 60 and x out. This becomes 60x. What is left from here is 1. What is left from here is minus x squared. And then I put it equal to 0. Okay, what are the possible roots here? So it gives me how many answers? 60x times 1 minus x squared is 0, yes? 3 answers, yes? One of them is 0. The other ones are plus or minus 1, yes? So this becomes, because if I put this equal to 0, I get x equals to 0. This equals to 0 means x squared is 1, so I get x equals to minus 1, x equals to 1. But can I be sure that all of them are right? Can I be sure that all of them are inflection points? Not yet. These are only possible candidates for inflection points of this function, if any. So I need to check if that's true or not. So I need to set up another table. Okay, so I have a table here. Again, the first row is as usual x. The last row is as before f. The middle row is f double prime. and I arrange the numbers I found in ascending order from left to right. So it is -1, 0, and 1. I immediately know what happens to my second derivative at these points. It definitely becomes 0 because I myself put the second derivative to 0 and got those numbers. But then you have to calculate these numbers using the original function. And that's not hard. For example, for 0, if I put it in the original function there, it becomes 0 again, yes? So if I put 0 in the original function, it becomes 0. If I put 1 here, it's also simple because x to power 1 is just simply x to power 3 is 1, so it becomes 10 minus 3, which is 7. If I put -1, this becomes minus 10, this becomes plus 3, so it becomes -7. Yes? Okay, if I want to know about the second derivative sign, I choose a random number on the left side, for example, -2, but be careful. You have to put it in the second derivative. And this is your second derivative. By the way, this is the factorized form of my second derivative. It is easier to understand the sign if I have it in factorized form. Okay, so if I choose -2 here, instead of x, this part becomes negative. This part also becomes negative. So then if I multiply negative by negative, it becomes positive. And if I choose a random number between 0 and -1, say -1/2, when I put it here, -1/2 times 60 is negative, but this is positive. When I multiply them, it becomes negative. If I choose a number between 0 and 1, for example, 1/2, this becomes positive, this becomes positive, that is still positive. And if finally I choose a random number after 1, for example 2, and I put it here, this becomes positive, this becomes negative. So the product becomes negative. So all of them are real actually, because this one here is concave up, here is concave down, here is concave up, and again here is concave down. So this means that how many inflection points I have? I have really 3 inflection points. Inflection point number 1, -1 and -7. Inflection point number 2 is actually my origin, the origin. And the inflection point number 3 is 1 and 7. These are the inflection points of my function. Okay. It is a good idea if we just draw the graph of these two functions using Geogebra, and then we learned last time, I think, that there is an instruction in Geogebra to calculate the inflection point directly. So that's also good to practice that one as well. So if we go to Geogebra now, let me just get rid of that. Let me draw the last one. It is more interesting. We have 3 inflection points. Let us see how it goes. So my function is y equals to 10 x to the power of 3 minus 3x to the power of 5, yes? So that is the function. Okay, so let me rescale it a little bit for you so that we can see it better. So this is the graph of the function. And then, so how many inflection points you see? Just intuitively, 1 is around here, 1 is around there, and 1 is here. By the way, what is this type of inflection point that appears here? Is also a terrace point, yes? So do you understand that this is the behavior of a terrace point? So at every terrace point is already an inflection point. How should I know that? The middle one. How should I know that? By calculation that the middle one is actually a terrace point. Because if you put 0 in the first derivative here, the answer also becomes 0. So this means that this is indeed a terrace point. So everything was correct, and we calculated all of them correctly. But let me just use Geogebra. We still don't know if -1 is the exact point and if 1 is the exact point. But I think in Geogebra, we can go and ask about inflection points, yes? So inflection points, so let us see, because usually GeoGebra has surprises for us always. So here I have to write my polynomial. Okay, so let me just type it because I don't know. X to the power of 3, and then, so I don't really understand why GeoGebra do this to us. So if I go here again, inflection point, so this is my inflection point, and then I just click on it. And then I start typing my polynomials as 10x to the power of 3, and then I go down, minus 3x to the power of 5. Okay, so I don't know why GeoGebra, okay, provided all of them, but I do not see them here. How can I see them? I don't know. Okay, I see all of them now. So actually they are highlighted on this graph. So these are exactly the inflection points of this function. So that's also good to know about this syntax that you can use to calculate. Okay, now let us go back to the notes. There is also another function here. I'm not sure if I have provided the example. So let me first give you an example that don't get it wrong. If you just calculate the second derivative and put it equal to 0, you might get the false answer. The simplest example that comes to mind is this example. So let me just write f of x equals to x to the power of 4. So assume that I give you this function and I ask you the same question. Find all possible inflection points for this function. So what you do according to the recipe, what you do, you just calculate the first derivative, extremely simple. You calculate the second derivative, which becomes 12x squared. But then what do you do? According to what we do, we put this equal to 0, and what do I get? I get 0. That is my warning here. If you don't follow the next parts and stop here, you might get this impression that x equals to 0 is the inflection point. But that is not the case. Why? Because the recipe does not end here. The recipe tells you you have to continue. Of course, sometimes you are so lucky, and even if you are careless, you get the correct one. But this is not always reliable. So what you need to do, you need to go and set up the table, as I told you. So x, f double prime f, you put your candidate here, the second derivative is 0. Here, the function itself is also 0. But look, if I ask you what is the sign of the second derivative to the left of 0, what do you say? I choose a random number, say -1 here, and put it in the second derivative. But the second derivative is 12 times x squared. So regardless of the value of x, 12x squared is positive, either on the left or on the right. It doesn't matter which number I choose. So this means that here, the function is concave up. In the passage of that point, it remains concave up. So even though I found this answer, but that is a fake one, because the concavity did not change in the passage of this point. So what is the answer to this question? What are the inflection points for this function? There are no any, yes? Because there is no any. Because we have only one candidate, and that candidate does not work. So this means that there are no any inflection points for this function. And if you go back to GeoGebra to confirm that, we can draw the graph of this one very easily. So if I ask you, so let me get rid of them. Okay, so I would write y equals to x to the power of 4, and that is your function. And I don't think there is a trick of rescaling. If you want, I can rescale it in any way that you like to, but still you don't see any inflection point here. Yes, so that is what I want you to be careful about. So if you just take the second derivative and then put it equal to 0 and expect that what you get is indeed an inflection point, It might be the wrong impression. Sometimes it is not working. And because the function might be complicated, you cannot guess if this is correct or not. You have to check if this is correct or not. Okay, so let us see what we can do now. No questions? Thank you.